Welcome everyone to this event, the Young Scholars Exposure event, the second event by the JB Scholars Professional Development Forum. And today we have two speakers, Annesya Banerjee and Sayantan Dutta, and we'll introduce them briefly in a bit, but we'll probably first introduce our reviewer for today's session, Professor Soumyajit Mandal. And so Professor Soumyajit Mandal is an associate professor at the University of Florida, USA, and he is a JB Scholar of 1998 batch. So welcome, Professor, and we'll definitely would like to hear hear your reviews about the talks that Annesya Banerjee and Sayantan Dutta would give. So thanks a lot for your time.
Yeah, definitely look forward to it.
So the first speaker will be Annesya Banerjee. She is a senior year undergraduate student at Jadavpur University, and she's a JB Scholar of the 2017 batch. Her talk is on making robots to listen, current developments, and future prospects. So, Annesya Banerjee, would you like to start, your presentation?
Sure. So is my screen visible to everyone?
Yeah,
Yes.
we can see it.
Okay.
Yeah. If you want to put in this slideshow mode, that would be probably better.
Is this fine?
Yes.
Okay. So now, robots and intelligent system has become an integrated part of our society. And even in the near future, many of us will be surrounded by this system. And with this increasing demand of these robotic systems, researchers are now working to make this system even more compatible with humans. And in that regard, sound and auditory perception is an important parameter for these robots. And with that, I, Annesya Banerjee, am here today to take you through the journey of making robots to listen, current developments, and future prospects. So first, we'll be understanding how human brains process audio and sound and what are the different information being instructed in our brain. And then we'll move to the same concept for the robotic systems and how this happens in the robot brain. However, robotic systems are never accurate and perfect. And in the auditory context also, the robotic system has several drawbacks. So we'll be discussing in detail the drawbacks and the possible ways to improve their auditory perception. And in that regard, I'll be very happy to talk about some of the contributions from our research team in this work. And finally, I'll conclude this talk by discussing the future prospects of this technology. So let's get started. First, we'll be understanding how humans actually listen. So many of us may think this listening capability as something taken for granted. However, listening is a very incredible mechanism in the human body. Whenever we hear some sound, that sound passes through our ear anatomy and then finally goes to the brain by passing through the external ear canal, then to the middle ear bones, and finally to the cornea, where the sound waves are transferred into electrical stimulation that stimulate our auditory nervous system, which finally stimulates the brain. However, depending on what kind of sound we're listening, the properties of the sound like pitch, tone, and all the musical properties related to a sound, the different parts of that auditory system of our brain is getting excited. And based on that, our brain understands exactly what kind of sound it is. Now, when the brain gets the sound, what does it do with that? So what are the different information that the brain extracts from it? Definitely, it's the semantic content. So suppose if someone is talking in front of you, your brain tries to understand what exactly that person is saying, because based on that, you have to respond. So that is what semantic content analysis is. However, apart from semantic content, our brain also analyzes the temporal information related to a sound. If I say a situation like there are two persons speaking in front of you and you're the third person listening to them, without even looking at the speaker, you can easily understand which person is speaking at what time and when that person is talking and the other person is talking. Even if the two persons speak simultaneously, our brain can easily understand without seeing which speaker is saying what. And this is what is the temporal information of the sound, which our brain continuously extracts from this audio. However, this is not yet done. There are also geometrical or spatial information being extracted from the sound data. So what does that mean? Now, in case of temporal information, the information was related to the variation of time. However, in case of geometrical information, it is related to the three-dimensional space around us. So the brain tries to understand exactly from which location that sound is coming, and it also tries to separate the different sounds coming from the different locations around us in the three-dimensional space. And these are the tasks that the brain does continuously throughout our lifetime until and unless we lose our hearing ability. And it's really interesting to think that even when we're not thinking about hearing something or we are not conscious, and even in situations when we are sleepy, even then our brain continuously does this complicated job. This was about human brain. But what is the scenario for the robots and the machines we're talking about? So how does their brain understand this kind of auditory information? So that we'll be understanding now. But in this regard, we also should understand that for robots or the intelligent system, their brain is the processing unit. So all the data that are being gathered by their senses is transferred to this processing unit, that is the robot brain, and it analyzes that data and further extracts information based on which the robotic system decides what to do next. And in auditory context, there are mainly two different tasks that the robot brain does. One is speech perception. So if I talk about devices like the Amazon Alexa, Apple Siri, or the Google Voice Assistant, they are excellent in understanding speech. So whatever we are saying, who is saying, that is recognizing the speaker and also responding to what is being said in a form of human speech. These are the capabilities that these devices have acquired over the last few years, and they have been doing it perfectly, almost like human communication. And this is because of the development in technologies like deep learning, natural language processing, for which these devices have gathered such an excellent speech perception. But in case of understanding audio and sound from a location-aware point of view, these devices are not that brilliant. In terms of location-aware auditory perception, what I mean is, suppose a situation like a roadside scenario. So there are people talking in a road, and also there are car horns, the sound of the bus, and also maybe there is the bell ringing of a cycle. So there are all the different sounds, but we humans can easily understand which sound corresponds to what system and from which direction it is coming. So it's not a difficult task for we humans. However, for robots, it's very difficult to understand which sound is what. So which one is the sound from the bicycle and which one is the sound from the car, and exactly from which direction that's coming. So it's really a difficult task for the robot brains to analyze. But the question here is that why are the robots so poor at doing this work? So over the last few decades, we have seen the robotic system being some incredible jobs that we have never thought of. But what is the reason that the robots are so poor at this kind of location-aware auditory perception? And that we'll be discussing next. But before that, we have to understand what is the audition system in a robot. So for humans, we have our 2 ears using which we analyze the sound and through which the sound passes to the brain. But what is the system for a robot? Now, in case of devices like the Alexa or the Siri, they have microphone for capturing sound data from the surrounding environment and analyzing that. But a single microphone is not going to work for a location-aware auditory perception. And that's why, motivated by the human system of binaural ears, we have to move to this kind of artificial binaural ears. So they have the two different ear-like systems, like two microphones that capture the surrounding sound, and based on that, it produces location-aware information of that auditory input. But two microphones are not always sufficient, and that's why you have now moved to 8-channel, 16-channel, and even 32-channel microphone arrays. Like this one is a 32-channel microphone array of larger size, this is a spherical array, and this is a smaller version of this 32-channel microphone array, which are being used for sophisticated robotic systems for incorporating this location-aware auditory perception. Now the question is that why do we require two microphones and not one? So just refer to the simple geometric representation. We have two microphones, mic 1 and mic 2, and we have a source case. So our task is to identify the location of the sources with respect to the microphone array system, mic 1 or mic 2. Now from this geometry, we can very easily extract the angle theta at which the source is located. Here it should be noted that we are considering situation like far field scenario where the source is located at a significantly large distance. So the sound waveforms are no longer spherical, but they have turned into planar waveforms. And as the sound waveforms reaches this microphone array, and from this distance and time input with respect to the microphone array, we can easily extract the value of this theta using the simple trigonometry we are used to with the sine cos rules. But this is a very ideal scenario because in real scenario, we have the reflection, reverberation, and multi-path propagation of sound. So if we consider a scenario like a room there, the sound can reflect in all the different walls and can take multiple paths to reach the source, which is a scenario like this. And this, in this case of real scenario, two microphones are not going to be sufficient for a robotic system. And that's why we had to move from two microphone to multi-microphone, like a system like this. So this is a 3-microphone linear array system, but ultimately what we are doing is at a time we are choosing 2 microphones, and for that we are extracting the location of the source as the approach we did here. And finally, based on all the different pairs, we are clustering the final observation. So what we are doing is we are choosing a point where most of the observation is lying, and that point is finally referred to as the actual source location with respect to the robotic system. Now, based on the requirement of the robotic system and also the complexity of the problem statement, the microphone array can be placed in different configurations, and also the number of microphone sensors can be varied. Like this is the humanoid robot, now robot, and this is the head of this robot. So you can see like these are the red dots where the microphones have been placed, or the array configuration, but also the microphones can also be placed on the arms of this robotic system to identify the source location with respect to the robot itself. Again, in this case of ground vehicles, we don't require many number of microphones. So an array of 2 microphones is sufficient, which are located in these positions. And this is a system developed by our research team that we have been working on 8-channel microphone array like this one, which has been settled underneath the drone system. So based on the requirement, the researcher can change the position and configuration as well. However, audition is not the one single problem for robots having the location-aware perception. There is another cause, that is the ego noise. So what is this ego noise? We are very familiar with the typical noise that is produced when a motor rotates. So if we go to the electrical labs or the mechanical labs, we can hear that noise when a motor starts to rotate. And that same noise is produced when a motor in a robotic system rotates. So if we consider a drone system like this, its propellers rotate because of the rotation of the motors, but at the same time, it produces that typical noise, which we call is ego noise. Similarly, in case of this humanoid robot, the different joints move because of the movement of the motor system, and similarly, it produces the ego noise. But the problem with this ego noise is it masks completely the important sounds like speech, music, and any other important sound that can produce necessary information to the robotic system. And also the other problem is that the frequency spectrum of the ego noise and the speech or an important sound overlaps extensively, for which it becomes very difficult to separate the ego noise from the actual sound or the targeted sound. And that's why the robotic system cannot extract necessary location-aware information from the sounds that it gathers. Now, there have been several approaches for reducing this ego noise and also improving the location, source localization approaches in a robotic system. But over the last decades, most of the works focused either on improving the source localization using different robotic audition system or either improving the noise estimation part. But over the last few years, people are working on joint noise removal and localization, in which our group has also worked on. However, in these different approaches, we have to take care of different deciding factors like improving the accuracy in terms of localization and separation of the mixture of sounds. But at the same time, we have to reduce the complexity of the problem and computational time, and also reducing the power requirements and physical dimension of the entire system. Otherwise, the system cannot work as a real-time system and cannot respond in real time. Now, at this point, I'll be very happy to discuss some of the contributions from our research group. We have been working on a drone system with having this very accurate location-aware auditory perception, which we call as listener drone. So this is a kind of drone system that can be used for search and rescue operations where it can track the auditory sign of the victim, and from that we can quickly identify the location of the victim for the rescue teams. And in that, using the joint noise estimation and source localization approach, we have been able to very accurately identify the location of that victim in terms of the azimuth and elevation angles. Now, azimuth angles are the angles with respect to the X and Y plane, where the elevation angle is the angle with respect to the Z plane. And we have been able to achieve 2 degrees errors, within 2 degrees errors for the azimuth angle, while that for the elevation angle was only 4 degrees. And this has been a very successful development towards making the robots listen with location awareness. But at this point, I believe that after discussing so much about how we can improve the auditory perception in robots, what are the drawbacks and the possible improvements, you all have this common question that why is it necessary to make these robots to listen to sound with some location awareness? So what is the benefit or utility of doing so? And there are many such utilities. So the first utility is definitely improving the human-robot interaction, because audio is one of the very important signals for our communication. That's because audio is the only signal that a human can both perceive and produce. We can produce audio using our speech production system, while we can perceive audio using our hearing system. And that's why audio is one of the very important parameters for human communication. That's why when we want to translate to human-robot communication, we'd like the robots to listen to what we are saying. And that's why we need the robots to have this great auditory perception. But apart from human-robot interaction, there are also important parameters like improving autonomous robot navigation. So over the last few decades, we have seen robots having cameras and image processing algorithms as their vision perception, and they rely on this vision for understanding where to move and identifying their path for autonomous navigation. But consider scenarios like a night scenario or in a dark room. So what we do in a dark room, we don't rely on our vision, rather we rely on our sense of touch and sound. And that's exactly what we want to incorporate in this robotic systems. So what we want to have audio slam systems where this robot will navigate using its auditory perception. And also there is the application of search and rescue operations, which I have mentioned, like listener drone can also do. And apart from that, it's also an important application to use robotic systems in scene reconstruction and also exploring the unexplored world. So in situations where a person cannot go in remote areas like caves and mines, we can send easily a robot to explore those spaces and reconstruct that cave or that mine. But in that, we cannot only rely on the vision perception of a robot or the image processing, because there might be scarcity of light and the robot might not be able to do it properly. Even the research has shown that in case of scene reconstruction, audio-visual perception works better than only visual perception. And that's why having robots with extremely good auditory perception is really important. And the other interesting thing is that using audio, we not only can reconstruct the stream with more accuracy, but we can also understand exactly what is the materials composed of in the surrounding environment. So it can be really helpful for applications like mining and stuff. Apart from that, it's really important for robots to communicate among themselves. And for that, we cannot only rely on seeing each other. So the robots have to talk with each other when they're out of sight. And for that, they have to have some extremely good auditory perception. And that's why researchers are working throughout the world in making robots having auditory perception with extreme location awareness. Last but not the least, I'd like to thank my teammates and my professors, without the support of whom I might not be able to talk about this interesting domain so much. So thanks to them, and also thanks to the funding agency without whom we haven't been able to do all the research first. And lastly, thanks to all of you for your time and kind attention. I'll be very happy to answer any questions you may have. Thank you.
Thank you, Annesya, for the talk. We have some time for questions. So if someone has a question for Annesya, please, if you can type that in the chat window. If Professor Soumyajit Mandal also has a question, you might unmute yourself and ask it directly. And after the questions, we'll hear from Professor Mandal about his review for the talk, as well as answering the questions. So.
I think I'll let the others ask questions, and then I can ask them later when I talk about the.
Sure. So if others have questions, can you please ask? Can you please type them in the chat window? We'll wait for a bit for your questions. Professor Papianundi, did you have something? I think you're muted. Sorry, we cannot hear you. Can you unmute yourself?
Can you hear me now, Debarghya?
Yes. Yes.
Okay. Annesya, it's a very interesting talk, though I have no experience in this field, but I appreciated you saying this thing. But you were talking a little fast, say it rather slowly so we can follow it. Otherwise, it is very, very good. New topic for me at least, not for you. Thank you very much, Annesya.
Thank you, ma'am. Thank you so much.
Okay, so I think we can hear from Professor Mandal as well of his comments.
Yeah, so I think it's a very nice talk. Congratulations. I think it's well delivered. A couple of suggestions. One would be, if the audience were to look for more information, generally they would like to have some references. So, you can think about including a couple at the bottom of the slides, when particular topics come up, so they can look for more information. For example, if you have your own work, you can cite that. Even if it's not your own work, you can still add a couple of review articles, references to those somewhere in the presentation. So that would be good. In terms of the content, yeah, it's very interesting, and I've done some work on cochlear modeling myself, so I found the fact that you started off with the biological analogy kind of interesting. So yeah, I think it was a pretty nice presentation, a good introduction to the field for people who are not familiar. I did have a question for you, which is, where do you think we're going next with this? What sort of developments do you expect in the next few years?
Like as I said, so most of the developments in the speech perception field that has been that has reached some comparison to the human. So that's one part. So it's definitely based on the application area. So what application area that robotic world is going to work on. So if it's something based on simple speech communication, then I think that it's quite a bit saturated. Definitely there are ways to improve. But if we are going for this kind of and localization applications. So I believe, like as I mentioned about that eco audio slam. So that is the work that has started just 2-3 years back. So the first work on this audio slam was done around in the year 2015 or 2016. So I believe in the next few rounds because in the past robots, the thing is that the robotic system has relied on one particular signal or the other. So it's either some image data or some computer vision thing, or it's either audio. But I think at the future or the near future, it's going to be sensor fusion. So we are going to implement different sensors, and we are extracting different information from all the sensors, because all the different applications. So if you consider about the application of images and computer vision, they have their advantages as well as disadvantages. And also for the audio system, it has its advantages and disadvantages. So in the near future, the works is going to be like taking the advantages of all the systems and using all the inputs from the different sensors and gaining some accuracy that the past system with on only a single modality of sensor has not been able to achieve. So I believe that's going to be the next phase in this kind of course.
So thank you. Yeah, one more question I had was on the ego noise. So that's an interesting problem. It's not just for robots. Humans have the same problem. So you are less sensitive because you're always listening to your own voice, right? So there's this thing called a stapedial reflex, where there's a muscle which pulls one of the middle ear bones away from the eardrum when you're about to speak, and you anticipate yourself. So a few hundred milliseconds before you're going to speak, this thing is the stapedial reflex is active. So I wonder if that's something of interest for robots as well. So because ultimately the motion of the robot is under the control of the software, so it could actually predict when when auditory perception is required, and control the noise, as it were, ahead of time to reduce the interference. So I wonder if anybody looked at that.
That's true, but I think like having robots to work in the same domain is, I think, easier, because in human body making some changes is a bit different. So we don't have exact control on the middle ear bone, so it's going to be a very difficult task. But I think the learning that we may have from this robotic system can help us in maybe developing devices that will help in not exactly controlling the middle ear bones, but like say, like the kind of noise we have, the noise cancellation microphones now. So we may have some kind of microphones or like some kind of speakers or any electronic devices in the future, maybe that will help us in reducing this kind of noise without controlling the middle ear bone. So this is a kind of expectation that I have, but I'm not very sure about it.
I was asking about the applications to robotics. So for example, in a robot, you do have control over your motions. So, when when you do need good auditory perception, perhaps the software can actually control the motion or stop the motion temporarily before the sound perception even happens, so that ego noise is less of a problem. I mean, I'm saying that's what the body does. So maybe the robot can do something similar. So the software could be written.
Yeah, I think like your question is not very clear to me yet. So if you can explain.
Well, what I was saying is, if you have a problem with self-generated noise, since the noise is self-generated and under the control of the same controller, you can actually turn it off or reduce it, on purpose, right?
Yeah.
To reduce the problem. I mean, in a sense, the body does something like that, so it's analogous. That's all I was saying.
Yes. So while doing the work on the drone, we also encountered some things like that. So the drone system that we had, it had extensive ego noise. But when finally we talked to different
Annesya, we cannot hear you.
I think I'm very sorry that I got disconnected for some reason. But so what I was saying that even for the drone system also, we can control the ego noise itself, so definitely. But it's very much really dependent on the material that we are using. So like the kind of robots or the drones that generally being used in today's world, that's related to the carbon fiber thing, but it has been tested in mechanical labs that if we go for devices like 3D printed system, then it's very easy to reduce the ego noise to quite a big extent. So because the 3D printed material itself absorbs some component of the noise, so that's why it's possible. So, yeah.
Thank you again.
Thank you, sir. Thank you so much.
Thank you, Professor Mandal. I have a couple questions and maybe a little bit of comment. So essentially, to me, it seemed like, so what you presented, Annesya, essentially, I did not know about this robotics and, the audio and visual perception, etc. So it was a good learning experience for me, but it wasn't entirely clear to me what your contributions were. Essentially, I mean, for sure, there was this one slide where you mentioned that this is your contribution, where you had this the differentiation, I think, between azimuth and elevation, right? For the drone, if I'm correct. Are you still there?
Yeah.
Okay, so what I wanted to know is in the background where you mentioned that previously it was just the source localization and separately done from this noise elimination, whereas recently it has been it's being addressed jointly. So can you possibly elaborate a bit more, because I don't know about it, elaborate a bit more on what exactly, like, let's say, what the field is in that, or was existing in that area. It was your group the first one to address this problem in a joint scenario, or you came up with a new algorithm, or what you used some algorithm, some standard algorithm, but made changes or added something, and how the performance, improved, or how that fared compared to what was the state of the art, something along those lines.
I'm sorry, just I'm keeping the video off because I have some network issues.
Sure.
Otherwise, I'm just addressing your question. So yeah, so as I said that mainly that two reasons. Two main aspects are related to either improving the source localization or either reducing the noise part. So most of the works if you say about in the last 10 to 15 years, they have worked on either keeping the noise as it is. So they didn't work on improving the noise estimation part or reducing the noise from the exact or extracting the exact audio from the noise plus audio data. So they just kept the noise as it is, but worked on improving the source localization in noisy scenario. And the other approach was that they didn't work on improving the localization. So they just worked on a very basic localization algorithm, but they work on improving the noise estimation. So the better you estimate the noise, the better would be you able to remove that noise from the combined noisy data. So these are the main two approaches that people have worked on in the last 10 to 15 years. But the joint approach, it is not definitely we are not the first team to propose this joint estimation, but what we did was proposing an algorithm that is in case of this kind of robotic systems, we have to keep in mind that these are going to work in real time. So we have to keep the thing that everything is going to be on board. So we don't have the offline processing provisions here. So we cannot do like first collect some data, then process it on the system, and then give it to the system back, or the robot back. So it's not the case here. So everything has to be in the real time on the onboard processor that the robot or the drone have. So that's why what algorithm we have proposed is able to do this kind of processing, this joint optimization in real time. So where is the difference between the previous works on joint estimation and the work we have proposed is that in the previous works on joint estimation, they were not that good in this onboard processing, but we proposed a kind of you can say this is a kind of lightweight algorithm which can be implemented in the onboard processor, and that can work in real time. So just to give you an idea of how fast it can work. So if we are working on an audio segment of say length p millisecond, then our algorithm can extract the noise and remove the noise from the system and produce it back a clear or almost clear sound within the time span of p by 2 milliseconds. So we are trying to achieve this faster, or we want to make this algorithm faster for real-time implementation. So that is mainly our contribution in this joint implementation of noise estimation as well as localization. So did I answer your question?
Yes, thank you. And I would definitely say that I don't know if you already mentioned these in your talk, but I would definitely say that these are very important salient points of your contribution. So it was not mentioned in words in the slides, but I think it'll be a lot better if you do highlight these aspects where you have like these are the quantitative metrics.
Actually, I just wanted to, sorry.
Yeah, the quantitative metrics of, we are scientists, so we would better understand that how you have improved the state of the art compared to what was existing. So in addition to when you said that your processing time is t over 2 milliseconds or something like that, in addition, I would probably be also interested to know that the existing algorithms which you said was not tuned as well for real-time processing. What was the time requirement for those? So then a comparative time analysis would tell me that yours is a more real time than the others. So do you have a number for that?
So it actually is not very straightforward. So it will depend on your application area, and like if I talk about the application area that our system approached, so that was identifying a location of a person using the sound. So in that case, we have to have an like when we're developing the system, so we have to have an estimate of what might be the possible separation between the two systems. So suppose the two possible sound sources are separated by a distance of say 10 meters, and I have a
Sorry, we cannot hear you again.
I think she got disconnected.
and I have a speed of say 10 meter per second. So that means that I have only 1 second for processing the thing. But if my the distance between the two sources is 20 meter per second, 20 meter, and my speed is 10 meter per second, then the processing time we have the processing time of 2 seconds. So it is very much comparative in the way that what we are doing. And if now on the other hand, if it is a ground robot and it's working in an indoor environment, so definitely the two distance is not going to be 10 meter or 20 meter. It's at max going to be 5 meter. But if it has a speed of say 10 meter per second, then we have only less than half of a second for the processing. So based on the application area, it will depend. So yeah. So that's why it's not exactly very much like we cannot compare exact with numbers with the other works that is already there in the research community. But it's just to give you an essence of what it does and how it does.
Right, I think Professor Mandal may have some more comments.
Yeah, just to follow up, I think I agree. I understand that the quantitative comparisons are a bit difficult, but like Debarghya said, we live with numbers, so anything you can do to make the comparison a bit easier for somebody to follow would be great. Maybe a table where you look at when you have columns with different earlier work versus your work, And you can put comments there, or when you talk about it, you can say, okay, this comparison's a bit tricky, but nevertheless, having that would help people understand, what the contributions are. So I agree with that. And that would have been good to add somewhere.
Okay, sure, sure. I will. Yeah, sure.
We have one last question from the audience, Sayantan Ghosh. So he is asking, listening, is it only limited to communicating, or is it also extending to controlling, as we tell children to listen, meaning to behave? Annesya, are you there?
Yeah, it's just going and coming the connectivity. So can you just please repeat the last part? So it's listening or communicating.
Yeah, you can also read it in the chat in case it,
No, there isn't any chat.
okay, so the question is it only, so when you said listening of the drones or listening of robots, he's asking, is that listening, does that mean it's only limited to communicating, or is it also extending to controlling, as if, like, you would, let's say there are multiple, what I'm assuming he wants to mean is, if there are multiple robots and you would want to control them in an array of robots, then how would you be able to do that, extending to controlling, as we tell children to listen, meaning to behave?
Yeah, so I hope that I have got the question correctly. So definitely it's, like if I talk about the systems like the Alexa or the Siri, so we already control it using our voice. So we say, hi Alexa, what is this? So it's a way of controlling. Now, if we want to control the motion of a robotic system using this sound, it's definitely possible. So if you have, say, 3 robots, you want to make the report see to go to some other place. So it's definitely possible. So what you have to do is similar to the Alexa thing. There should be some identification word so that the robot understands that if you are talking to that particular robot. So you can say that, okay, robot A, come to my side. But at the same point, there is the importance of having this location awareness. So when you are at the corner of the room and you're asking the robot to come to your side, then the robot needs to know that where you are located exactly. So it needs to know the location of your voice, and that's exactly what I was saying, that it's sound source localization. So exactly, for the controlling, it is possible, but for that we need to have the robots to have that location awareness in its auditory perception. So if the robots had that only speech perception, so if the robot would have only understood that the person is calling me, it had no clue that in which direction it has to move for going towards you. And there is the importance. So exactly, there is the importance of having this location awareness in auditory perception. So definitely it's possible. So I hope I answered this question.
Yeah, I hope so too. So thank you, Annesya Banerjee. And also thank you, Professor Mandal, for your comments, and everyone for asking questions. Also, Professor Papianondi, for your comments and question. So we can move on to the next talk, which is by Sayantan Dutta. So Sayantan Dutta is currently a doctoral student at Princeton University. He's JB Scholar from 2013 batch. And his talk will be on data-driven computational modeling of early Drosophila development. So Sayantan, would you like to start presenting?
Yeah, sure. Hi, good evening or good morning, everyone, and thanks Debarghya for the nice introduction. And I will talk today about part of my thesis work on data-driven modeling of early Drosophila development. So in the context of biology, what is development? It is developing a functional organism starting from a single cell. And in that process, the first step is generating cells, and multicellular organisms achieve this through the process of mitotic divisions. And our model system Drosophila goes through 13 rounds of divisions after the fertilization. In the 3 hours of time, it generates 6,000 nuclei through the process, and the first 9 rounds happen in the bulk of the embryo, and whereas the last 4 rounds happen in the surface. Now, after generating cells, they need to know what fate they will achieve, because all the cells have the same genetic composition. And this is done by the asymmetric distribution of signaling factors. So you can see a virtual embryo here, which is colored in different colors like red, green, and blue. And this denotes concentration levels of 3 signaling factors. And these signaling factors control the gene expression patterns of 1,000 genes. And these gene expression patterns denote the mechanical properties of the tissue, which ultimately direct large-scale cellular flows, which directs the morphogenetic deformation of the tissue that is folding to ultimately get a functional organism. Now, decades of work has been done on this system, and here are a few representative works. And my thesis aimed to build predictive models standing on the shoulder of these data sets. And my first project is on the first process that I mentioned, that is the nuclear division in the Drosophila embryo. And in the left hand side, we see a movie of early Drosophila embryo, and we see syncytial divisions. That is, on the same surface, the nuclei divides and the numbers multiply. And in the second column, we see 3 snapshots from 3 different densities in this tissue. And in the right hand side, we see a similar example from a non-living system, that is a colloid system, the structures in 3 different densities. And by looking at them, we can identify that there is a difference between these 2 structures. And how does this dynamics distinct? So by dynamics, I mean the change of structural order with respect to density. And to answer that, we basically ask 2 questions. How is this packing of nuclei in the tissue? How does the structural order change with density? And what is the simplest model that describes the formation of this tissue? And to quantify the structural order, we use a metric that is called radial distribution function, or G of R. So what does this metric mean? So given a particle at a origin, you count the number of particles at a distance R, and you find the density of the particle at a distance R, and compare that with the bulk density, and that will denote the structural order. And let me explain this by the example of the non-living material. So here is the material snapshot of the materials in the 3 densities, and in the second row there are the computationally generated structures in the similar density. And if we quantify the function, and we can see how do they transit as a function of density. So initially it looks like in a very low density, it looks like a step function. Then when the density increase, we see a peak, and in a very high density, we can see very sharp peaks, and there are multiple peaks. And we can see this is like equivalent to a gas to liquid to solid transition. But how does this transition looks in the non-living system? Again, here the color means from the lowest to the highest density. And if we quantify the G of R in these systems, we can see in all these cases, there is no long range order, because the G of R goes to 1 at long distance. However, the position of the peak shifts leftward as the density increases. And if we rescale the density with a inverse square root of density, all these peak positions collapse. And this denotes there is a characteristic length scale of the system which rescales with density. And to generate these structures, we use a force field model.
Sorry, Sayantan, I'm sorry to interrupt you a bit. Do you want to click on your play button? I think you're cutting off the top title of your slides.
Okay, so is this good now or no?
Not yet for me, but I don't know. Can anyone else comment?
Is
This is all right. Debarghya?
Okay, so let's continue.
Okay, yeah. So, okay, was anyone speaking anything? Okay, so yeah, so to describe the formation of the tissue, we use a force field model where like each nucleus is denoted by a particle, and each particle experiences two kinds of force. One is pairwise interaction and another is random force. And the pairwise force is a hardcore soft shoulder potential. That means if they overlap, there is a strong repulsion, but there is a diameter, there is a ring of diameter lambda around the particle where there is a soft repulsion. And we propose to get the rescaling that after division, the diameter of this shoulder rescales by a factor of √2. So density becomes twice, the lambda becomes lambda by √2. So this factor remains constant throughout the division, that is rho lambda square. Whereas the Brownian force that is the random force is a force in random direction with a magnitude denoted by the parameter zeta. So there are two parameters in the model, eta and this zeta. So we ask like, so for what value of this parameter we can get a structure that is similar to the real embryo, and we minimize the error between the G of R from the simulation and the experiment to get the minimum error. And we can find that at the minimum, when the error is minimum, the experiment and simulation are on top of each other. Next, we ask if we can generate the self-similar behavior as a function of density with this algorithm. And yes, we can do. So here is the rescaled G of R. So where so the distance is rescaled with inverse square root of density, the peak positions overlaps as we have observed in the experiment. And next we implement the same model on the surface of a prolate spheroid, and we generate a structure similar to the real embryo. And the benefit of this prolate spheroidal system is that this is geometrically very similar to the real embryo. So it gives us a platform for simulating the next events, that is patterning and morphogenesis. So what we have learned here, that nuclear packing in the embryo, in the Drosophila embryo, has a short range order, and the structure of the system is self-similar as the system progressively densifies. An adaptive force field model with hardcore soft shoulder interaction reproduces the similar structure, and we can create a virtual embryo that is a platform of further simulation of the events of patterning and morphogenesis. And next, I will talk shortly about the project on this patterning. And just to remind what is by patterning, what I mean. So giving the cells specific identity by the gene expression patterns. And I will talk about a specific gene expression pattern here. So ARC is one of the three signaling factors I mentioned that is expressed at the pole of the embryo, and it phosphorylates a factor called Capicua, which otherwise represses these genes like tailless and Hakabine. So if ARC is there, Capicua is not there, and these genes can only express them. And these genes are important for the embryo because in absence of them, the head structure doesn't form properly. And if they are expressed everywhere, we lose the segmented structures at the middle of the embryo. So this needs to be, so for proper development, both of them, they has to be expressed and expressed at a specific location. And we explore the system with a very specific experiment. So in the normal embryos, these factor is only at the pole, and the respective genes can only express there. But with a tool called Optosos, we can activate the gene at a ectopic location, that is the middle of the embryo where it doesn't express. So, and we can observe the gene expression patterns there. So on the left hand side, we can see a normal embryo, so there are no dots appearing. In the middle, we observe an embryo where we activate the system and keep it forever, and we can see these bright dots appearing, if you can follow. And in the last case, we turn it on for a specific time period, so the dots start appearing and then they decay. So we turn on these genes for a few minutes and then turns off. And in all the experiments, we collect data from multiple levels. So what is the concentration of Capicua, and how does the gene expression change as a function of time, and how the Capicua binds to DNA. And they are collected in wild type, the normal embryo, and the embryos where we activate this system artificially. But now the question is, how do we integrate all this data? Because these are separate pieces of information. And to do that, we use an integrated model where we use this mechanical model of nuclear division that I discussed in the previous part. Second, in each of these nuclei, we simulate a kinetic model where this signal gets activated and deactivated in response to light. And the molecule, this transcription factor Capicua, that gets in and out of nucleus and binds to DNA. And in all this localization, it remains in an inactive and active form. And the transition between these two states depend on the level of the signals, which is E. And given on how much of this factor is bound to DNA, the respective gene transitions from a transcriptionally inactive state to active state. So if there are more factors bound, the genes can't express and K1 is low, and vice versa. So we have a model which has a lot of parameters, as you have seen, this kinetic rate constants. Some of them we have direct experimental evidence, but there are 12 free parameters. But how can we estimate them? So we use the experimental data obtained to get the parameters, so sets, and so that the difference between the experiment and the simulation minimizes. And here, as this parameter set is a 12-dimensional set, we use a Markov chain Monte Carlo, not a gradient descent type of thing. So Markov chain Monte Carlo, using these Bayesian techniques, we find the parameter sets that can reproduce the experiments. And yes, we got a set of parameters that reproduce the experiment within experimental error. So the points with the error bars represent the actual experiment, whereas the solid lines shaded by the color bars represents the simulation. And so yes, so the parameter set obtained represent results that is similar to the experiments. But now what do we learn from these optimized parameter set? So these are the 12 free parameters, and these are 2-dimensional projections in the 12-dimensional space. And for some parameters, we can know exactly the values with some error. Like for example, for the rate of binding and unbinding. For the rest, we don't know the exact values, but we can see some trends. For example, like which order of magnitude they belong. For example, these two parameters, we can see a linear relationship, and so on and so forth. So this gives us the information about the individual processes going on in the embryo, which was difficult to explain, difficult to get from the individual pieces of data. Now, in the last one, I mostly talked about the temporal dynamics of a gene, but there are also spatial dynamics. And here is an example where this gene, this gene in green that is influenced by two of the signaling molecules. And with this model, we can identify the spatial pattern, again learning from the data, which I don't show for the interest of time, but from the experiment we can identify, we can again simulate the spatial region of expression as well as the temporal dynamics of the gene. And now next, as I said, like our virtual embryo is very similar to the geometry of the real embryo. We can use these genetic patterns to simulate this mechanical deformation. So what we do here, so these are the gene expression patterns, and we can set the contractility of the cells as a function of the gene expressed here. And we can, if we simulate the tissue with a vertex model simulation, we can simulate how it folds. So again, from this part, we have developed an integrated model that takes into account multiple factors, that is nuclear doubling, transcription factor dynamics, and gene transcription. And we demonstrate a framework to how to integrate different experiments and using these models, we can learn the rates of different processes, and which can ultimately lead to predictive models. And third, the similarity to the real geometry allows us to simulate the mechanical models of deformation. Now, what is the big picture of these exercises? So we can say these are the mini steps to build a virtual embryo. So in the left hand side, we see a work from a different group. So that shows how the nuclei generated in the bulk of the embryo reaches the surface. Then in the second row, work from my first study that shows how the nucleus spreads on the surface of the embryo. In the third column, we can see how different genes pattern this surface and ultimately how they fold. And so these are like mini steps towards the ultimate aim of a virtual embryo, where we will start from a single cell and we can get a fly out of a egg completely computationally. That will reflect the understanding of the system. And at the end, I will like to thank all my experimental collaborators in these projects, my postdoc mentors who have worked closely with me on these projects, all my external collaborators, and of course my thesis advisor, Professor Schwarzman, and the entire group for the discussion and the support. Yeah, and that's all I have for today.
Thank you, Sayantan. So we have one question from the audience, and if others have questions, can you please type them in the chat or unmute yourself and ask them. So the first question is that the particles that we are talking about, you may have answered it in some way. This was asked some time back, but the particles that we are talking about are the nucleus or cells of the developing Drosophila embryo.
Okay, so this is a syncytial tissue. That means the nuclear division happens, but the cell membranes build only after. So let me share my screen again. So yeah. So this is the schematic. So only the nuclear divisions happen in this time, and after all the nuclear divisions are done, then the cell membranes divide the tissue into multiple cells. If that is clear, yeah. If that does that answer your question?
Sorry, I guess that does. So Tathagata Vasu has a question.
Yeah, okay. Yeah, go ahead.
Tathagata, we cannot hear you. Do you want to speak out or type in the chat?
Am I audible now?
Yes.
Yeah, okay. So could you please go to slide number 26?
26, yes.
Yeah. Yeah, sorry, 23. So the MC plot one, I think it's 23.
23, yeah.
Yes. So on the transcription one, it seems like there is a little bit of phase shift. So are you using any kind of location parameter there for your MCMC simulation?
Look, so yeah, so what I understand is your point is like there is a difference between from here to here, right? So
yes, yes.
No, so in the model our transcription is like a very simple model, like K on and K off. So there is no phase shift, and this is the best we could get like from the MCMC. So yeah, we could not correct that. Yeah, we have identified, but the current framework doesn't allow that shift to.
Right. Okay. Okay. But so have you tried, like, I mean, just a suggestion, have you tried like incorporating some like location parameter? Because when you're doing Bayesian simulation, that location parameter may learn from the data and do that thing automatically, and I mean, you may get a tighter plot, I would say.
So by location parameter, you mean there is a so how do I take the initial condition or something? Yeah, or
Just like put something for the mean, so that way you
oh,
can learn.
Okay. No, I have not tried that, but yeah, that is a good idea. Yeah, I will try that. Thanks. Yeah.
Okay. Yeah. Anyways, that's a very nice talk. Thanks.
Yeah, thank you for the suggestion.
So another question. So is it like, I don't know how to pronounce it, syncytium at the beginning of development fused cell membranes with multiple nuclei?
Yes, that's it. Yeah.
Can you explain what that word means? I don't know.
Syncytium means like in a single cell where the multiple nuclei are there. So in general, in our idea of cell, like one cell with one nucleus, right?
Okay.
So, but if you have like multiple, so one example is like a muscle cells. We often see this, like there are multiple nuclei, but there is no cell membrane division. So what happens here is you start from a single nucleus. First, we divide all the nucleus, but there is no compartment, and this compartmentalization happens at the end. Yeah. So yeah, so this cell, there is no cell membrane at this stage. Like, I mean, there is only one cell membrane here, and there is no partition between these like individual nuclei. Yeah.
Understood. Thank you. So, Professor Soumyajit Mandal, would you want to put your comments?
Yeah, I think that's a great talk. Thank you. I had a question about the computation. So,
Yeah.
so how computationally expensive are these? And what do you have some thoughts on how these can scale? So, you're going from a Drosophila to, let's say, you want to simulate something larger. What is the feasibility right now? I mean, how long would these take if you want to go to larger systems?
Yeah. So for these like force field problems are something between order of so let me come here. So these kind of problems are something between order of n to order of n square, right? Because you have like technically you have interactions from all the nucleus, but as we are dealing with short range, we don't need to calculate the distance between everything, so we can improve our performance there. Like something to like 1.3, 1.4, not exactly n square. So for the periodic condition, it is like very, so for a like 1,000 cells, it takes like an hour or so. This is very fast. But for these things, when you need to calculate the distance along this surface, it takes a bit. So for the 6,000 cell system, it takes around a day or so. Like, I mean, with a single processor, no, with a 8 core. So yeah, with 8 core, it takes about a day or so.
How do you expect that to scale?
So this is n to the power 1.4 or something.
This is also n to the power 1.4. Okay. I mean, it's not too bad, right?
Yeah,
you can think about going to larger, significantly larger systems. So what are your goals next? I mean, with now that you're integrating these various models together, what do you want to do next?
okay, so one next thing we can do. So for example, this is we have done for a like one gene and a very simple networks, right? So for that we tried to, so the next goal is to do it for a like a more complicated spatial pattern. For example, some things like this, right? So this is one extension, and the another project, another thing direction I am working on is so working on these flows, like how does characterizing these cells, how do they flow. So for example, the approach we use here is particle image velocimetry. So we have this image, we unwrap them, and we do something called, so basically we get the velocity, get the displacement field of the from the image analysis, and then try to connect with these things, like how this kind of stress, I mean stress distribution can ultimately result in the displacement fields. And so this is another direction which I have not talked about in this talk, but yeah.
Thank you. Another question, I guess, was at this stage, are there any electrical phenomena going on, or is it all chemical? I'm just curious.
Not something I aware of. So there are, of course, some things like membrane channel and these things goes on, but I don't know of like a specific system where that is responsible for. But mostly this is a like chemical. So this is a mechanical patterns that generate ultimately this kind of movement. So yeah, so one is chemical and another is physical or mechanical, what you would say. So this force and the stress patterns, this is, we can say, like a physical or mechanical phenomenon.
I noticed that you had stochastic models in the gene expression part. So,
Yeah.
sorry. So how important in your view is the stochasticity there? I mean, is there a significant amount of randomness? Or
There is a significant amount of, okay, so this is to like generate, so for example, we observe this thing. So if you like look at this movie, you can see that like this is a real movie, not an simulated. So you can see that like all of these cells are not expressing. So I think like there is a significant amount of stochasticity, and there is no spatial. So we have activated the system throughout this box. I mean, even more in a more region, but still we see. So for a like a similar representation, we need this. Definitely we can coarse grain for some purpose, but yeah, that is not a like true representation. Yeah.
Thank you.
So, Professor Mandal, do you have any comments about how Sayantan may improve his presentation? So one of the aspects that we are trying to achieve through this exercise is to be able to present better to a broad scientific audience. So, do you have any thoughts on that for him?
I think, yeah, I think, for a broad audience, you need a bit more introductory material, I think. For some of us who are familiar with some of these concepts, okay, it wouldn't be hard to get started with what you're saying. But for For others, it may not be. So yeah, I mean, depending on your audience, if it's a broad audience, like in this case, JBNSTS is people from all sorts of backgrounds. Yeah, I would put in some more introductory material. For example, the question on, you talked a lot about later about the fact that this is a tissue with where a single cell basically with multiple nuclei. That part might not have been obvious to a lot of people at the beginning. But to you, it's obvious because you've been working on it for a long time. But others may not be. So yeah, and that would be my one major comment. I mean, and technically speaking, yeah, I mean, I would always put in something at the end on future directions. So you've gone this far, now what do you want to do next? That leaves people maybe excited about things to come afterwards.
Okay, thanks for this. Thank you.
Okay, so thank you, Sayantan, and thank you, Professor Soumyajit Mandal. Also, thank you, Monisha, for asking nice questions. Does anyone have any other questions, or we'll probably conclude today? Thank you, everyone for joining.
Thank you for organizing.
Yes. Sure, of course.
Yeah.
So Molly is the primary organizer. She was here at the beginning, but she had some other work that came up, so that's why I did the hosting for today. But she primarily does the hostings for these events. All right, so thank you once again, everyone. Thank you, Annesya, and thank you, Sayantan, for your presentations. Definitely, I learned new stuff today. Also, thank you, Professor Mandal, for your time and your valuable opinion on both of the talks. And so we'll definitely be in touch. And thank you, everyone, for joining. We'll hope to see you in future events as well. Thank you.